This adapter's not working. I'll try this, thank you. This is, I tried it on the other adapter's working.
Oh, sorry.
No, it's fine.
You don't need.
All right.
Okay, so next speaker is Kimball Germane, and he will talk us about posteriori environment analysis with pushdown data.
Okay, so often when you port a compiler optimization from a first-order language to a higher-order language, you have to contend with some of the subtleties that a higher-order language introduces. And so for one class of optimizations, these optimizations are sensitive to the environment subtleties of higher-order languages. So in order to enable these optimizations, you need an environment analysis. And pushdown delta CFA is an analysis that if you give it a pushdown control flow analysis, it yields an environment analysis. And it's unique in the area of environment analyses in that it doesn't require the cooperation of the control flow analysis. It doesn't operate in conjunction with it. It operates solely on the pushdown model that it produces. So for this talk, I want to focus on higher order inlining, both to motivate the need for environment analysis and illustrate how we apply pushdown delta CFA. So let's start in the first order world. We've got these function definitions f and g, and we want to inline at the call to f in the body of g. And because this is a first order world, we don't need to worry about any environment issues. We can simply substitute the body of f into the call, making sure to bind the arguments. In a higher order world, we'll have these definitions. We're going to run into some subtleties, and we'll build up a list of conditions that will ensure the safety of the inlining. So since we're in a higher order world, let's imagine that these definitions are in the scope of some variable, that variable appears free in the body of f, and that the call to g is indirect. So the first question we need to answer is, or let's suppose that we want to inline h. So the first question we need to answer is what flows to h? Is this inlining even sensible? Because multiple, or closures over multiple lambda terms could flow to h, and of course, in that case, it doesn't make sense to inline. So that leads us to our first sort of condition or criterion, which is if we want to inline a lambda term at a call site, then only closures over that lambda term can flow to the operator. Let's say that this question is answered by the control flow analysis, and let's suppose that f does indeed flow to h and is the only closure that does. Now in general, f could come from anywhere in the program and have any free variables in its body. So we need to make sure that those free variables, when we substitute the body, are in scope at the call site. So that leads to the second condition, which is the free variables of the lambda term we're inlining, they have to be in scope at the call. So you can see in this example, z certainly is, so we might be inclined to do the substitution. But as we have demonstrated, this is not safe, or as we've done, this is not safe. And I have an example that I want to go through to demonstrate why. We're going to come back to this example a couple times through the talk, so it's worth just looking at what this program does. So the first thing it does is it defines a function f. It calls f, binding the result to g, and then it calls f again with g as an argument. So at the first call to f, it passes 42 and false, binding them to x and h. It checks this condition, which in this case is false, and we evaluate the false branch. This is lambda term with a free variable, so it evaluates to a closure, and that's what gets bound to g. The second call to f passes 0 and this closure, which get bound to x and h. This time the condition is true, and so we proceed to this call to h. Now we can see that this call to h will yield 42, but notice that this closure is the only closure to flow to H, this call site, and that the free variable x is in scope here. If we perform this inlining, and then I'll beta reduce just to make it clear, we can see that the result of the call to F will no longer be 42, but will be 0. We've changed the meaning of the program by performing the inline, which means it's unsafe. The issue really is that at this call to H, there are two bindings of X that we need to keep track of. One is the binding in the environment of the call, and the other is the binding in the environment of the closure. So this leads us to the third condition, which we've got to make sure that those bindings are the same. Now, we can solve this problem by evaluating this program on a machine that keeps track of binding times. In this machine, environments wouldn't map variables to values, they'd map variables to times, and we would have a heap where we could direct lookups to find the actual values. So we're going to step through this program a little more explicitly, paying attention to binding times. We'll consider the evaluation path. The states are annotated with the current time, and then this will be the heap. So we begin by, we sort of enter the main function body of the program. We evaluate the closure that's going to be bound to F and bind it to F. We can see that in the heap, that this binding of F made at time 3 was added. So we make this call, proceed as we did before, and if we look, we can see X and H are not bound to values, they're bound to times. They're both bound at 5. When we evaluate this closure, the closure captures not just the value bound to X, but the time. But the important thing is when we finally come to this call again at H, that we can see in the environment of the caller, X was bound at time 11. But if we look at the closure bound to H, in that environment, X was bound at 5. So we've successfully distinguished between these distinct bindings, and we can see the inlining would be unsafe. Now this was in the concrete. We might be tempted to simply abstract this machine, abstract the time domain and the value domain, and perform the same sort of thing, make the same sort of comparisons. This is not safe in general because our time abstraction might conflate distinct times. And this is true even if we use a more common representation for times, like a sequence of call states. But this idea, and an even bigger problem is that not all abstractions even maintain a notion of time. Some push-down control flow analyses omit time altogether when they build their push-down models. But the idea is a good one to sort of look at when bindings were made in evaluation and compare that. And so instead of using times, we're going to use the structure of evaluation. And this structure comes from the fact that every state in evaluation plays a particular role. And this role is determined entirely by the syntax of the procedure or of the call. And I've put this syntax in CPS just to make it very clear. The only times in which variables are bound is when we enter a procedure or when we return from a procedure that might bind an intermediate value. And in the other cases, procedures are exited when we reference a continuation, and once we exit a procedure, we'll pop a stack frame. And then the other cases are when we actually push a frame and need to return. So this is the full evaluation path of the example program running the machine. And we, instead of looking at the times of each evaluation state, let's look at the classification. And simply from this classification, we can decompose the path into its invocations. And by that I mean that these states These red states all are states evaluating the main body of the program. These green states are all evaluating first call to F, they're all in the body of F. This is checking the condition in that first call. And these yellow states are all evaluating in the body of the second call of F. Now the shape of this path and the color groupings are determined completely by roles that these states play, by these classifications. So when we abstract our states, as we will eventually, we can do this exact same decomposition. So now that we have a decomposed path, let's look at this problem of distinguishing between the bindings of X in the call to H and in the caller environment and in the closure environment. So first, let's look at the caller environment. We're going to use this notation here to denote the state in which X was bound in the environment of this call state. And we don't know much about this, but we do know the most recent place that variables were added to the environment. That's the predecessor of the state. And so this is a continuation call. No continuation or no variables were bound in the call, so X was not bound here. So we're going to skip over the call. And now we're simply looking for when X was added to the environment of this state. We perform the same, or we use the same reasoning, and just go to the predecessor. X is in the formal parameters here, so this is where it was bound. So this is so the state in which X was added to the caller environment is this state. We do the same thing to find the binding X in the closure environment. We're going to do it in two steps. First is to figure out when the closure was made, because the closure captures the environment. Once we determine state with that closure environment, then we can continue to resolve the binding of X to get where that binding was made. So to resolve a birth state of a term, we look, if it's a variable, we need to figure out when was the variable bound. And so we just resolve the binding state in the same way that we did for X. And here H is in the parameter list, so this is where it was bound. Now, now we need to see what was bound to it, so we need to match its position up with the argument, with corresponding argument in the caller. So H is in position 2. We move to the caller, and we're going to look at the second expression. That was G. We're looking for the birth state of G, once again a variable, so we just follow this process again. G's bound here, so it resolves. Once again, we're looking at the caller to see what was bound to it. And here we finally have a lambda term, and that means that this closure that we're looking for was born in this state, and so this state contains the environment that we're interested in. So that resolves. So we're looking for binding state of X, and we simply walk back just like we did before. This resolves. And so we have that the binding to X in a closure environment was bound in this state, not the same state as the binding to, in the caller environment. And so without any use of time, we've successfully distinguished between these two binding states. Now, this program, incidentally, is the control flow graph for an abstract interpretation of the example program. But in general, we're going to have forks and cycles and joins due to recursion. So I just want to quickly look at one of the issues that comes up with recursion, or a few of them. It's not important to understand what this program does, but we want to inline at this call to F, and we want to inline this lambda term, which has a free variable y. So this is the control flow graph. It has a lot of cycles in it, but we sort of proceed in the same way, and we're only going to resolve the binding of in a caller environment. So we go to the predecessor. We sort of use the same reasoning, but here we sort of have a problem. The first is that we're at an entry state, the procedure entry state, and y is not in the parameter list. That means that y was free in the currently active, in the body of the currently active procedure. And that means that we need to find the birth state of the active procedure. So we need to resolve that. The second complication here is that this state has two predecessors. And so we'll take the predecessor that keeps us in the red. And we'll sort of perform the same sort of reasoning. Now, this map is a recursive reference. And so we'll treat it as a lambda term, as it would have been if we had used a fixed point combinator for recursion. So this birth resolves here. And now we're seeing this familiar bind-find pattern. So we're back at the call state, and we're at the same stage of resolution. And so we just continue this process naively, we would go forever. But what we're really looking for is a fixed point of this resolution. And so the fact that we've gotten back to this entry state in the same stage of resolution as we were before is good. It means that the recursion doesn't really influence sort of the binding structure of the program. So now we'll go to the predecessor, in the green, and this usage of map is not recursive, so we'll treat it as variable. So we need to find where it was bound. Sorry, this is going so slow. Anyway, the point is that we can successfully distinguish between bindings even when we have cycles and forks and joins to contend with. Now, what I've shown you, all of this, is really only half the story. And the other half is there's work, there's a control flow analysis, an environment analysis called Delta CFA that has a really rich environment theory, and it's based on frame strings, which are stack changes. And we combine our resolution framework with this machinery so that we can justify these optimizations without doing as much work, and it also enables us to do some heavier weight reasoning about environments. And thank you. If you inline in a tight loop, if you're able to inline in a tight loop, I think you see quite a big performance improvement. I'd say in my preliminary tests we found maybe like 35–40% time improvement. You were asking about memory. A tight loop would. The original Delta CFA work had this really elaborate machinery, and based on knowing what stack change occurred at each transition, we show that we can recover that same stack change just looking at the structure, and so we're able to just leverage their results. We can, in the paper, we base it off of CFA 2, which after its initial development, they added support for call CC. And in our paper, we discuss a little bit about how to leverage that. And the short answer is that as precise as the CFA 2 analysis is, we don't lose any precision. Because if you jump over the call CC call, the environment is the same. And so we're able to recognize that.
So in the examples you gave at the beginning, on the line, you showed that you can distinguish different call to the function. Have you studied some situation where you run abstraction or use information? Where you fail?
Yeah.
In understanding this.
Yeah. It fails mostly when the control flow is dictated. Sort of like imagine if the number of levels of recursion you took was dependent on some natural number in your program, and we fail there because we basically lose all of the precision of the natural numbers in the abstraction. But then it's not as bad as it seems, because often in those cases you wouldn't be able to inline anyway, because you wouldn't have a fixed natural number going around, if that makes sense.